Hello, welcome. First, let me give a big introduction to myself. I am the author of the book, Discovering Imaginary Numbers in Everyday Life. Subtitle, The Popularization of Complex Numbers. This book is for general and educational readers. There is another book from me that's specifically for preteen learners. The book name is Having Fun with Complex Numbers. Subtitle, A Real-Life Journey for Upper Elementary Students. These books were written to spark curiosity, discover new ideas, and make complex topics feel simple. Through this video and the others in plan, we will explore the book's key ideas together in a clear, friendly, and visually engaging format. This episode's title is How to Explain Complex Numbers to a Preteen. Since it's for explaining to kids, here we tend to use simple wording and language. The episode is designed to make learning feel effortless. So let's dive in and see how these new concepts connect to everyday life. Spatial perspective for points and numbers. We live in a 3D world. Like this box, everything around us has 3 dimensions: length, width, and height. If a thing is not shaped like a box, we use a pretend box that wraps around the thing. The pretend box then helps us measure how big the thing is using length, width, and height. Since we live in a 3D environment, it's important to understand the relationship between numbers and the space around us. As we will see, numbers represent dots called points. It's helpful to have the right spatial perspective among points, 1D lines, 2D planes, and 3D space. Here, the box is 3D. The flat surface here is 2D, like a part of a plane. The edge here is 1D, like a line segment. Points form a line. This means a 1D line can be broken down into points. A point is the most basic math object. We can't break it into smaller pieces. Points are the building blocks in math. Because of this building block, we can use a single number to show exactly where a point is on a line. The power of a moving point. Every shape is formed from points. Just one teeny dot called a point. That's all it takes. Move it around like a pencil tip. Wherever the dot goes, it can draw shapes, build graphs, create patterns, and even make designs. Number line. A number line includes 0, the middle of the line, and the starting point. It's also called the origin, where everything begins. Right side, going right from the origin. Numbers grow up. These are positive numbers. Left side, going left. numbers go down. These are negative numbers. Position points have a direction. Imagine a map. All the places on the map are just dots. They don't have a direction. But if you pick a starting spot, like an O on the map, suddenly every other spot has a direction. We call our starting spot the origin. Every other spot is a position point. A position point is represented by a position vector or arrow. Here we will use the kid-friendly word arrow. The arrow has both a direction and a length. The direction that tells which way to go, and a length that tells how far away the point is from the origin. Every number on the number line has a direction. Now, let's think about a number line like it's a map. The 0 is our starting spot, or the origin. Every point on the line is a position point. Every number is like an invisible arrow stretching from 0 to that number, having both a direction and a length. If a point is to the right of the 0, its arrow points in the positive direction. The number is its arrow's length. If a number is to the left of 0, its arrow points in the negative direction. The number's distance from 0 is its arrow's length. Since the number line is one-dimensional, all numbers on it are called 1D position numbers. Multiplying and stretching unit arrow 1 to reach any point. The number 1 is special. It's considered a unit arrow having length 1 and pointing to the positive direction for a number line or an x-axis. Multiplying a number by 1 doesn't change its arrow at all, but if you multiply by a number greater than 1, it stretches the arrow and makes it longer. If you multiply by a positive number less than 1, it shrinks the arrow and makes it shorter. Here, the unit arrow is stretched by multiplying number x. Since x stands for any number, the math move makes the arrow stretch to reach any point on the line. Line motion versus spin motion. In real life, things don't just move in straight lines. They also spin. For example, a car can go straight, which is a line motion, or it can turn, which is a spin motion. We have used math moves like multiplying to slide a dot along a number line. That's like a car moving in a straight line. But what about spinning? What's a number? Can we make a new one? In math, the word number doesn't have one exact meaning. Long ago, people invented numbers to solve real-life problems. First came whole numbers to count things like 3 people or 5 apples. Then came fractions to show parts of things like half of an apple. Later, we got negative numbers to show things like owning 3 coins in a trade. Each new kind of number was invented when people need it. And guess what? All these numbers have one thing in common. We can use math moves on them, like adding or multiplying. So far, math moves only make a point go along a straight line on the number line. It's natural for us to ask, can we spin a point with a math move? We will explore this next. Ruler for measuring distances. On the number line, numbers represent the positions of points, and vice versa, the positions of points represent numbers. The difference between two numbers indicates the distance between the 2 points. In real life, we use a ruler for measuring distances. Protractor for measuring angles. The concept of angle is used to describe curved shapes or spin motions. An angle is formed by two lines that meet at a common point. The angle measures the amount of turn between the two lines. It's often measured in unit degrees, which is the unit we use here. The protractor is used to measure angles. This is the starting line, which is at angle 0. This line and the starting line form an angle at 10 degrees. This line and the starting line are on the same straight line. The angle formed is 180 degrees. Right in the middle, this line and the starting line form a right angle at 90 degrees. Left spin of unit arrow 1. To get a feel for the angles and the changes, here is what happens when arrow 1 spins left around the origin for a full circle. Starting at 1, there's no spin yet. The angle is 0 degrees. Reaching the top of circle, the arrow points straight up. The angle is 90 degrees. At -1 on the left side, the arrow has flipped. The angle is 180 degrees. Returning to the start, the full circle is completed. The angle is 360 degrees. Number circle. On the number line, we move dots left or right using numbers that measure distance. That's a great idea, so let's copy it with a number circle, where dots spin left or right on a flat surface called plane. Here is a number circle. It's a unit circle with radius 1. A number line cuts the circle into 2 parts. The center of the circle is at 0, and the number line goes straight through it. Just like we say left side and the right side on the number line, we say top side and the bottom side on the number circle. The top side is above the line. The bottom side is below the line. On the number line, we measure how far a dot moves from 0. On the number circle, we measure how much it spins. Starting from the point at 1, which has an angle of 0 degrees. Angles on the top side are positive from 0 to 180 degrees. Angles on the bottom side are negative from 0 to minus 180 degrees. The wonder of flipping arrows. -1 times -1 equals 1. Let's explore a math trick. Flipping arrows. Multiplication can stretch an arrow. In fact, it can also flip the arrow. Let's see what we get with a flip of a flip. That is, a double flip. In math, the process is written as -1 times -1. Step 1. Start with 1. That's an arrow pointing right. Step 2. Multiply by -1. The arrow flips left. So, -1 times 1 equals -1. Step 3. Multiply by -1 again. The arrow flips back right. So, -1 times -1 equals 1. When we flip an arrow twice, it ends up pointing the same way it started. That is, a double flip brings you back to positive. Clues of math move for spin. Let's look at some clues that can help us figure out how to show spinning using math. 1. Sliding on the number line. When we multiply a number, it stretches arrow 1 and makes the dot at 1 slide along the number line. In this example, arrow 1 is stretched by multiplying 3. That's a helpful hint. We may then ask, can we use multiplying to make it spin by an angle too? 2. Spinning on the number circle. Now, let's spin arrow 1 by 180 degrees. It flips around and points the negative direction. So it becomes -1. That's the same as multiplying by -1. 1 times -1 equals -1. As we can see, spinning by 180 degrees and multiplying by -1 do the same thing. So we can use a special symbol like square bracket 180 to mean spin by 180 degrees and write 1 times square bracket 180 equals -1. 3. No spin at all. If we multiply by 1, the arrow doesn't change. No spin. That's like spinning by 0 degrees with the symbol square bracket 0. 1 times 1 equals 1, and 1 times bracket square 0 equals 1. So spinning by 0 degrees is just like multiplying by 1. Nothing changes. This gives an exciting hint. If we can spin by an angle, we can use a symbol like square bracket theta to stand for that angle, and then do math like 1 times square bracket theta. Let's explore this idea next. New kind of numbers. Square bracket theta. In fact, the simple square bracket theta represents a new kind of numbers called rotational numbers or spin numbers. The symbol for spin number theta turns an arrow left by theta degrees. In the case of spinning arrow 1 on the number circle, 1 times spin number theta means spinning arrow 1 by theta degrees. As shown in the figure, arrow 1 spins by angle theta and points to this direction. The spin maker, it needs a target. As a matter of fact, a number can't stretch or spin anything all by itself. It needs something to work on, which is called a target. First, let's look at a stretching example. We have an arrow that's 3 units long. If we use the number 2 to stretch it, the arrow becomes 6 units long. This is written as 3 times 2 equals 6. In this case, the arrow 3 is called the target, and the number 2 is the stretch maker. Now, let's talk about the spin number theta. It's like a spin maker, but just like regular numbers, it needs a target to spin. If we do spin number theta times p, it spins arrow p to the left by angle theta. The target is arrow p. If we don't say what the target is, the default is unit arrow 1, which points to the right. In the illustration here, arrow 1 spins by 1 spin number 90 to point up. A negative angle makes the arrow spin right. Here, arrow 1 spin by 1 times spin number minus 90 to point down. The direction pointer. Let's explore more about the spin number theta. It's not just a spin maker, it's also a direction pointer. Here in the figure, spin number theta spins arrow 1 by angle theta. After the spin number theta becomes a new arrow that points in the direction of that angle. So it's not just spinning, it's showing us the direction. That's why we call spin number theta a direction pointer. Multiplying spin number theta spins arrow 1 to a new direction. Do this for all angles, and we get a full circle of arrows pointing every direction. That's our whole number circle. Spin magic. When multiplying feels like adding. Let's see an interesting, unique property of spin numbers for multiplying. First, spin number theta 1 turns arrow 1 to become the arrow 1 times spin number theta 1 that points to this direction. Then we use spin number theta 2 turns the arrow to reach point P. The total angle for the two turns is theta 1 plus theta 2. Now, let's make a big turn by spinning arrow 1 with the total angle. That immediately reach the point P. In math, we can write this as spin number theta 1 times spin number theta 2 equals spin number angle theta 1 plus angle theta 2. As we can see, two spins are like one big spin that adds both angles together. Isn't it amazing? Multiplying turns into adding. The right angle spin maker. We already know that 0 and 180 degrees are special angles. They match with arrow 1 and arrow -1. It's natural to think that the angle right in the middle, 90 degrees, is also special. Let's look into it. Arrow 1 is on the x-axis. It points to the right. Now, when we use the spin number 90 to turn it like 1 times spin number 90, the arrow spins by 90 degrees, so now it points straight up onto the y-axis. The new arrow is still 1 unit long, but now it's pointing up. We call it the y-axis unit arrow, and we write it as square bracket 90, which is just another way of saying 1 times spin number 90. The spin number 90 makes a perfect right turn. We call it the right angle spin number, the right angle spin maker, or the right angle spinner, and we use the shortcut symbol I for it. I equals square bracket 90. So I is both the right angle spin maker and the y-axis unit arrow. Showing the right angle spinner. The right angle maker or right angle spinner I does two cool things. One, it spins an arrow by 90 degrees. Two, it points in a new direction, exactly 1 right angle away from where it started. You can show this with your own body. First, stretch one arm straight forward, like you are pointing at something in front of you. That arrow is your arrow 1. Now, spin your arm so it points straight up to the sky. That new arm position is the right angle spinner in action. It took your first arrow and turned it 90 degrees. So, your arm pointing forward is arrow 1. Your arm pointing up as the new arrow after the spin is I. Finding any point on a map with math moves, polar form. Now, let's explore how to find any point on a map with math moves like multiplying. Number r is a regular number on the number line called the x-axis. It points to the right. Multiplying number r by spin number theta makes it reach point capital P. The point capital P can then be represented by lowercase p, which is set to r times spin number theta. the lowercase p is a number. Since any point capital P is represented by a position vector or position arrow bold capital P, it's natural to call the lowercase p a position number or specifically 2D position number in polar form. With the 2D position numbers, we can find any point on the map or plane. Finding any point on a map with math moves, XY form. Now, let's explore another way of finding any point on a map with math moves of adding and multiplying. The point capital P is represented by position arrow bold capital P. To reach the point, we use two arrows, P sub x. The first arrow slides from the starting point O to x on the x-axis. P sub y, the second arrow, goes straight up from x to the level y. In math, that's written as arrow P equals arrow P sub x plus arrow P sub y. Arrow 1 is 1 unit long along the x-axis. To get to x, we stretch it x times, so P sub x equals 1 times x. The eye turns arrow 1 and points upward. We stretch it y times. Therefore, P sub y equals y times I. When we add both stretched arrows together, we reach the point capital P. In math, this is written as lowercase p equals x plus y times I. It represents 2D position numbers in XY form. This way, we can also find any point on the map or a plane. 2D arithmetic or 2D math moves. Finding points with math moves on a map or a big flat surface called plane. We can use math moves to find points in two ways. Polar form r times spin number theta. XY form x plus y times I. Moving points with math moves. On a plane, we can also use math moves to move a point in the following ways. Spin. Multiply by a spin number theta to turn the point around. Stretch. Multiply by a number to make the point go further out. X slide. Add the x part, x, to slide the point sideways. Y slide. Add the y part, y times I, to slide the point up or down. Here, we only mentioned the two math moves of adding and multiplying because they include the effects of subtracting and dividing. As we know, subtracting a positive number is the same as adding a negative number. This converts subtraction into addition, like this example. 5 minus 3 is the same as 5 plus negative 3. Also, division can be converted to multiplication, like this example. 3 divided by 2 is the same as 3 times fraction 1 over 2. Spinning and stretching work the same for points and arrows. A point's position can be shown using an arrow. When we stretch or spin the arrow, we are really changing the point's position. In practice, we don't draw the arrow. We just talk about the point itself. So, instead of saying stretch and spin the arrow, we say stretch and spin the point. Example of 2D arithmetic. 2D math moves. Let's try out an example for 2D arithmetic. Start from 3 on the x-axis. Spin it by 30 degrees. We then get 3 times spin number 30 and reach this point. Stretch it by 2. Now we have 2 times 3 times spin number 30, which equals 6 times spin number 30. We arrive at this point. Slide it right by 2. That is, at 2, we have 6 times spin number 30 plus 2 and reach here. Slide it up by 3, we add 3 times I and have 6 times spin number 30 plus 2 plus 3 times I and reach the position here. Let's wrap it up. There are 2 basic number types: regular numbers or real numbers x, spin numbers theta. The followings are formed or constructed by the 2 basic number types. The right angle spin number I is the spin number 90 for angle 90 degrees. The number 9 is formed by regular numbers x. The number circle is formed by the spin numbers theta. 1D position numbers are formed by regular numbers x, p equals x. 2D position numbers, which are also called complex numbers, are constructed from regular numbers and spin numbers. In polar form, the position numbers is written as r times spin number theta. In xy form, the position number is written as x plus y times I. Benefits of new approach to complex numbers for preteens. We have explored complex numbers in a new way so that a preteen can actually get it. This new approach to complex numbers, specifically designed for preteens, in this video and the book have the following benefits. 1. Let kids see the big picture and take control before diving in a sea of numbers and being overwhelmed by endless numbers and teeny details. 2. Discover key concepts naturally with real-world connection. 3. Visualize numbers and math moves. Our brains work better when we can see things in position or in motion instead of just thinking about numbers in our heads. 4. View from a higher dimension perspective than 1D. We live in a 3D world and view things every day on 2D screens, such as books, computers, and phones. It's easier to understand concepts in 3D or 2D than in 1D. 5. Let kids build confidence as they go. Fresh ideas, formulations, and extensions for complex numbers. If you want to get fresh ideas, new formulations, and extensions for complex numbers, this book is recommended. It's suitable for teachers, high schoolers, and beyond. Thanks for watching.